Hello, welcome to this video, lesson 1-2. We're going to go ahead and find limits of piecewise functions. Now, you may have not worked much with piecewise functions in your earlier classes. These are just functions defined by pieces, hence the term piecewise functions. We'll go ahead and we'll look at an example of piecewise functions here in a moment. But what I really want to go ahead and recap, the thing that you must remember the most when dealing with limits is that for a limit of a function, here f of x, to exist at x approaches c, it only exists if and only if the limit from the left is equal to the limit from the right. So the limit of f of x as x approaches c from the left has to be equal to the limit of f of x as x approaches c from the right. Okay, and again, so this means the limit exists if and only if the limit from the right equals the limit from the left. Okay, and sometimes you'll see people abbreviate it as this: the left is equal to the right, or the left is not equal to the right, if they're kind of denoting why a limit does not work. Okay, so remember, limit from the left has to equal the limit from the right. Checking the left and the right side limits is easy when given a graph because we can visually see it, but it's not always obvious when working with equations or in analytical form. And for a continuous function, if I have nothing breaking up the function at a certain point, we do not need to worry about the left and the right side limits because they're continuous, because they're approaching the same value. We'll go ahead and see this down below, but those are very, very easy to analytically solve for. Now, one common type of function that we see throughout AP Calculus is the piecewise function. The piecewise function. College Board loves the piecewise function. Okay, now what are piecewise functions? Well, piecewise functions are functions built from pieces of different functions over different intervals, and that's the part that really trips people up, and it's not too complicated. Because of this, they will appear throughout the course in a variety of ways. But the important thing is that laws of limits still apply, and mainly the limit from the left has to equal the limit from the right for the limit to exist. So example number 1. We're given some functions here, f of x, g of x, and h of x. Now they're all piecewise functions defined and given below, and they say use the functions to evaluate the following if possible. So first of all, we're going to go ahead and work with the function f of x, and I just want to talk about a piecewise function, what it is. So here we have a function f of x, and you'll notice I have a linear function, 2x minus 3. Okay, and it is defined over the interval x is less than 0. So any x values or any domain values less than 0, you're going to use that function. We have a secondary function, x squared plus e to the x. Ooh, getting crazy with the exponentials. And it is defined as anything greater than or equal to 0. So at 0 and to the right in the domain, we're going to go ahead and use that bottom function. Okay, now limit questions are a favorite with piecewise functions because we have this idea. Does the limit from the left equal the limit from the right? So here's a classical question. What is the limit of f of x as x approaches 0 from the left? So I'm coming from the left of the 0. Well, I'm going to use the top function because my domain is x is less than 0. So approaching 0 from the left, I'm going to use 2x minus 3. Well, this is very easy. One-sided limits, I can just go ahead and I can evaluate. I can plug in 0 to see what value it is approaching there. It's from the left. It's a one-sided limit. I don't care about the right side. So I can evaluate 2 times 0. That's 0 minus 3 gives us negative 3. So the limit of f of x as x approaches 0 from the left is negative 3. Okay, now they ask, what is the limit of f of x as x approaches 0 from the right? From the right of 0. So I'm going to use the bottom function, x squared plus e to the x. And again, this is a one-sided limit, so I don't have to, I know it's continuous. It's going to approach that value. So I can go ahead and plug this in. So 0 squared plus e to the power of 0. This gives us just 1, right? 0 squared, 0. Anything to the power of 0 is 1. Okay, so the limit from the left, -3. The limit from the right, 1. How about C? What's the limit of f of x as x approaches 0? Well, we just found the limit from the left. We just found the limit from the right. So if they don't equal, it does not exist. And again, the reasoning here is that the left does not equal the right. D, what is f of 0? What's the function value at 0? Well, hopefully you're paying attention to the domain, and you'll see, what do I use for 0 exactly? Well, I'm going to use the bottom function because the domain is equal to 0 there. It's equal to 0. So I can go ahead and I can plug in 0. That was x squared plus e to the x. So e to the power of 0. So f of 0, the function value, is 1. Okay, I would like you to go ahead and try E and F on your own at this point. I'll ask that you pause the video, try to calculate the limit of g of x as x approaches 1 and the function value at 1. You can go ahead and unpause once you've tried this, but I'm going to go ahead and talk through these videos, or through these examples. Okay, E, I'm going to go ahead and use g of x. So the limit of g of x as x approaches 1. Well, if you take a look at this function, notice it's broken up at 1. For less than 1, I use the top function. For greater than 1, I use the bottom function. And then they have a third function in the middle that's specifically at 1. Remember, for limits, I don't really care what happens at 1. I just care about from the left and the right. Do the left and the right meet? So what we're going to go ahead and do is I'm going to first, in order to calculate this, I'm going to say, okay, what is the limit of g of x as x approaches 1 from the left? I want to figure out, what about 1 from the left? Well, that's 4 minus x squared, so 1 squared. So this gives us 3. So the limit from the left is 3. Okay, how about the limit from the right? The limit of g of x as x approaches 1 from the right, I plug in 5 times 1 minus 2, and this gives us 3. Hey, the left and the right, they're equal. They're both 3. Right on, right on. So our answer is 3, But notice the function value, part F, it says, what's g of 1? Well, g of 1, if x is 1, the output value here is 5. So the answer here is 5, right? That would be a removable discontinuity. We'll talk about those actually in the next video, or the next lessons. Okay, we have a hole there. All right. Ooh, think you're starting to get it? Here's where we're going to switch it up on you. Okay, G, it says, what is the limit as x approaches -3 of h of x? So I'm going to go ahead and I'm going to use the function h of x, which is up here. And this function is interestingly defined. We have a function on top where x is not equal to -3. Everywhere except for -3, we're going to use that function. And then below, at -3, the value is 0. Okay, so if I'm going to go ahead and use this for the limit from the left and the right, I mean, they're both going to go to that value. So can't I evaluate, right, for the limit from the left? And it's the same function. So what I'm going to go ahead and do here is I'm going to say, okay, what is the limit as x approaches -3 of h of x? Or not of h of x. I'm going to do the top. I have a fraction. Whenever I have a fraction, I'm cautious because I think something's going to happen here. So of x squared minus 9. So what happens when I plug in negative 3 here? We get negative 3 squared minus 9. Oh, isn't that 0? That's 0. Okay, now I'm going to do the denominator. The limit as x approaches negative 3, and then the denominator, that was x squared plus 7x plus 12. Okay, so if I plug in here, we get negative 3 squared plus 7 times negative 3 plus 12. What does that give us? We get 9 minus 21 plus 12. Oh, this is also 0. This is also 0. So I have what we will talk about further in another video. 0 over 0. This is indeterminate. I can't determine anything. 0 over 0. That tells us nothing. But what I can do is I can go to this function up here, and I'm going to rewrite this. X squared minus 9. Isn't that x minus 3, x plus 3? And x squared plus 7x plus 12. Isn't that x plus 3, x plus 4? Oh, it is. And if I have stuff top and bottom, that goes ahead and that cancels. So really, that is x minus 3, x plus 4. Now, what you should remember from Accelerated Math 3 is that you have a hole there. When things cancel top and bottom, this is what we call a hole. We have a hole there, okay? So I'm going to reduce that, and then now I'm going to use this reduced function in order to calculate the limit, okay? So if I go back down here, I'll just continue my work down here. So the limit as x approaches negative 3, and on top we had x minus 3. X minus 3. Okay, so negative 3 minus 3, that gives us negative 6. Okay, and then the limit as x approaches negative 3 of the denominator, which was x plus 4. Right, I'm just using the numerator and the denominator here. X minus 3, x plus 4. And I'm doing them separately because if I get 0 over 0, bad things happen. So I'm setting this up for future success. We have negative 3 plus 4. This gives us 1. So our limit is negative 6 over 1. Negative 6 over 1, which is negative 6. There you go. So there's the limit. Ooh, that one was a pain in the butt. Don't worry, we'll do more just like it in the next lesson. Okay, and then they say, what is h of negative 3? Well, the function, the piecewise function at negative 3 defines it as 0. So our answer, our function value is 0. Okay, so let's go on and do some kind of abstract application with this idea that we have developed. Example number 2. Let k of x be the piecewise function defined above where c is a constant. So it's just some constant number. Don't try to get thrown off by c. It's just some variable. Find the value of c such that the limit of k of x as x approaches 2 exists. Okay, so I'm going to use this function, and they tell us that the limit as x approaches 2, it exists. It exists. Okay, well then that means the limit from the left of 2 and the limit from the right of 2 have to be equal. Okay, so if I'm using the limit from the left of 2, well, this function is defined 0 to 2 with this function. Okay, and then the limit from the right of 2, well, x is greater than 2, that is this function. Okay, well, if that's true, then they both have to be equal. So if the limit exists, 7 minus c of x, that's equal to x plus 1 squared minus 5. And we need to solve this. Now, you may be saying, hey, there's multiple variables there. Yes, but in this case, what's x? What value are we approaching? 2. So I can go ahead, I can rewrite this. 7 minus 2c is equal to 2 plus 1, that's 3, squared, that gives us, well, I'll just do this. 9, which is 4. So 7 minus 2c is equal to 4. And then isn't that something that you solved in 8th grade? Yeah. I'm going to go ahead. I'll subtract 7. Negative 2c is equal to negative 3. Thus, dividing by negative 2, c is equal to 3/2. There you go. A basic idea. The limit from the left has to equal the limit from the right. Okay, let's go ahead and introduce a wonky, funny looking graph, something we haven't looked for or studied before, but it appears in AP Calculus all the time. The function f of x is equal to the square root of x over x. Again, it appears often on the AP exam, and you need to memorize this. Wow, that looks really, really funny and really, really freaky. Maybe you haven't worked a lot with absolute value signs. Just remember, absolute value, it makes everything positive, everything positive. Additionally, with this structure that you should notice is that you have the same thing on top divided by the same thing, x over x. Well, what if x is 2? What's 2 divided by 2? 1. What's 3 divided by 3? 1. What's 9 divided by 9? 1. Everything is going to be 1 because it's the same thing divided by the same thing. The output is 1. Well, hold on a second. What about negative numbers? If I plug in a negative number, negative 2, the absolute value of negative 2, is a positive 2. Divided by negative 2, well, that's negative 1, right? And just to illustrate this, let's use 3. Absolute value of negative 3 divided by negative 3. Well, this ends up turning into a positive 3. And we get negative 1. Okay, so the idea here is that everything is 1 for function values to the right. If they're positive, if I plug it in, I'm going to get a positive 1. If my input values are negative, I get a negative 1. Now, there's one culprit here that is restricted. I cannot plug in 0, right? I have a discontinuity at 0. That causes problems. So how does this graph look? Well, I'm going to go ahead and show you here on Desmos. Here is the graph of the function. And you'll notice I have a discontinuity, a jump discontinuity at 0. Okay, and everything to the right is 1, everything to the left is 1. Okay, you need to go ahead and memorize that. So I'm going to go ahead and just draw a quick sketch of a graph. Okay, and I'm going to say here's 1, here's negative 1, and I have an open circle, right? It's undefined at 1. And then to the left, looks like this. Anything of this structure looks just like this. It does not change. Well, it does change. I'm going to change it on you in a second. But it has that same setup, okay? All right, example number 3. You need to understand how to graph transformations of this function. And the good news is it's the same transformations that we've been working with in Accelerated Math 1, Accelerated Math 2, Accelerated Math 3. All the graphical transformations, regardless of where you study, they're the same. So let's go ahead and look at example A. Here I have the absolute value of x minus 2 is equal to x minus 2. Well, here, this is what, at least if you've studied here at my school or in my class, we have an h value, which is a positive 2. And we're going to the right 2 units. So the graph, it's exactly the same, right? Because anything divided by itself, x minus 2 divided by x minus 2, it's 1. Well, that absolute value holds that numerator positive, okay? And then the denominator is going to alternate signs depending on which side of 2. So here's 2, okay? Here's 1. Here's negative 1. So at 2 in this direction, I'm going to the right. And then on the other side of 2, I'm going to go to the left. There's that graph. Don't believe me? Here we go. I'm going to turn it on Desmos. Boop. And there it is. Okay. So just notice that's the same graph shifted to the right too. All right. B. K of x is equal to 3 times x plus 4, absolute value of x plus 4, divided by x plus 4. Hey, cover this up. Isn't that same graph that we just saw? And didn't we just say this is an h value? but this time it's -4. That means we're going to the left, okay? And we also have a multiplier. Sorry, that was my phone. That's Chewbacca. We have a multiplier of 3. So A is equal to 3. Well, that's going to give us a vertical stretch factor by 3. Okay, so let me go ahead and draw a quick X and Y axis. I'm going to the left, -4. So here's -4. Okay, and then I'm going to end up stretching to 3. 3 and -3. So then my function looks like, let's make it red up here. I'm going to go this direction, and down here this direction. Now, sometimes too, you may be unsure of your graphs. Like, did I get this right? Test points, plug in values. Like if I plug in -5, what's k of -5? Well, if I plug that in, we get 3 times the absolute value of -1, so that's a +3, divided by -1. So 3 divided by -1. -3. And I got it right. Okay, let's double check on Desmos. Make sure I'm not screwing up. Boom. There it is. There's our graph. So it's the same structure. It's a unique function that, again, AP, that College Board loves to use, and they'll use it a lot. C, pause me. Please pause me. I want you to attempt this graph on your own. I'll show you the answer here in a second. All right. So in this case, we have an H value that is 3. You should have shifted 3 units to the right. And then you should have noticed you were dividing by 4. This is an A value being divided by 4. So you have vertical compression, right? So instead of multiplying to 3, you should have been at 1/4. So a quick sketch of this. Here's a +3. And again, I'm going to go here and here. And then the height of this is 0.25 or 1/4. And then the same down here, right? -0.25. Okay. And just to confirm, here we go. See, shifted to 3. We still have that discontinuity. And then the height is at 0.25. Okay, you're taking everything, you're dividing by 1/4. Okay, so let's go ahead and answer an AP question. Let's get our point for the day, or our 1.2 points for the day. So when given a problem involving one of these functions, sketching a graph first will allow you to quickly and easily find the answer. Whenever you have the setup, always just do a quick sketch of it, right? And you see my graphs are not elaborate. They are not like beautiful or, you know, gonna win any awards, but they give you enough to give you information. So from the 2014 AP exam, 16, the limit of the absolute value of x minus 3 divided by x minus 3 as x approaches 3 from the left is, okay, well, I'm gonna go ahead, I'm just gonna do a, quick sketch. Schwarberg told me, do a sketch with this. Hey, I'm shifted to the right 3 units. Here's 3, and I know the function looks like this and like this. All right, it's the same thing divided by itself. So the heights of these pieces are 1 and -1. Okay, now I have a graph. Isn't this just like the easy lesson yesterday? The limit from the left is -1. B is the answer. Ta-da! You got your AP point for the day. Hey, hopefully in this video you learned something or a lot about piecewise functions, and you found out how to find limits from piecewise functions. The limit from the left must equal the limit from the right. Catch you in the next one. Give me a thumbs up, like, subscribe. Thank you.